Hey everyone. In geotechnical engineering, getting our results right isn't just academic. It can be the difference between a safe design and, well, a catastrophe. So today, we're going to dive into one little setting in PLAXIS that is so critical for failure analysis, but it's one that a lot of people just overlook. It's called arc length control. And believe me, you're going to want to understand this. So here's a question I think every engineer needs to ask themselves. Have you ever had a simulation just stop cold? It fails to converge, and you're just sitting there scratching your head wondering, did I actually hit the failure limit or is something else going on? Or, and this is the scary part, what if your simulation looks fine, it seems totally stable, but it's actually hiding the real point of failure, a point that's much, much lower than you think? Okay, to get to the bottom of this, we've got to look at how PLAXIS actually applies loads in the first place. It really boils down to two totally different ways of doing things. You've got your standard load control, and then you have the more sophisticated arc length control. And as you're about to see which path you pick, well, it completely changes the answer you end up with. All right, check this out. This image right here just nails the whole problem. The top curve, that's your normal load control. The bottom one, that's arc length control. Now, they both start off looking pretty much the same, right? But just look where they end up. It's night and day. We're not just looking at two different paths here. We're looking at two totally different stories of what failure actually looks like. So what is the difference, really? Well, think of normal load control like a battering ram. You just tell it, hey, apply this much load, and it just tries to plow ahead. If it hits a wall and can't find a solution, boom, it just stops. It has no idea what happens after that peak load. But arc length control, it's more like a skilled climber. It's constantly asking, okay, how much load can the system really handle right now? It feels its way along, tracing the entire path, even when the material starts to weaken and the load it can carry actually goes down. So, you might be wondering, how on earth does arc length control manage to trace that entire complicated curve when the other method just throws in the towel? Well, the magic is all in its iterative process. Fundamentally, arc length control is an adaptive procedure. It's not just mindlessly pushing the load forward. No, it's smarter than that. It adjusts both the load and the displacement at the same time. Remember that climber analogy? This is it in action. It's carefully finding its footing on a really treacherous slope instead of just trying to sprint straight to the top. And because it does that, it can actually get over the peak and see what's happening on the way down. Okay, so here's the play-by-play. The algorithm takes a step, applies a bit of load. Then it checks, are we stable? And here's the secret sauce. It then adjusts its path. If it senses the material is starting to give way, it can actually back off and decrease the load to find the next stable spot on that curve. And get this, if it has to back off 5 times in a row, PLAXIS goes, aha, this is it, this is failure. It's basically a super smart built-in failure detector. Okay, I know this is a bit in the weeds, but why does this one technical detail matter so much? Well, it all comes down to the holy grail of our analysis, right? The factor of safety. Getting that number right, that's everything. That's the whole ballgame. And you don't have to take my word for it. This quote is straight from the PLAXIS documentation, and it's brutally clear. It says, without using arc length control, the failure load is overestimated. Let me say that again, overestimated. What that really means is you could be sitting on a factor of safety that's dangerously high and just wrong. So let's go back to our graph, because this just drives the point home. See curve A again, the load control one? Look where it stops. It doesn't even make it to the top of the mountain. It just gives up partway through the climb. But now look at curve B, our arc length control. It beautifully navigates right over the top, finding that absolute maximum load. That little peak right there, that's the number you actually need. That's your true failure load. So the takeaway here is simple, and honestly, it's the most important recommendation in the source material. For any analysis where you're trying to figure out a factor of safety or just investigating failure in general, you should always use arc length control, period. It really ought to be your go-to, your default setting. Okay, so if this thing is so great, you're probably thinking, why isn't this just the default for everything, right? Why would you ever turn it off? Well, as it turns out, there's one really big exception where you actually can't use it. If you've spent any time doing consolidation analysis in PLAXIS, you've probably seen this. You go to the settings, and the option for arc length control is grayed out. You can't even click it. The software just turns it off for you. So what gives? Why would it stop you from using what we just said is the more accurate method? Well, the reason is actually a fundamental conflict in the math, a real logic puzzle. See, consolidation analysis is all about time. And in those calculations, the stiffness of your material actually depends on the time step you pick. The key is you have to decide that time step before you even start the calculation. But we just learned that the whole superpower of arc length control is figuring out the step size during the calculation as it goes. So you see the problem? You can't have one thing depending on another thing that hasn't been figured out yet. It's a classic chicken and egg situation. So PLAXIS just says nope and disables it so you don't get a garbage result.
So let's boil it all down. The key takeaway is really simple, but it's super powerful. When you're doing a safety analysis, pushing your model to find its breaking point, arc length control isn't just a nice to have, it's pretty much essential for getting an accurate answer. But when you switch over to consolidation, just know that it's turned off for a very good reason, and you got to keep that in mind when you look at your results.
And that really leaves us with one final big question to chew on. We just saw how one single, kind of hidden setting can completely change the answer to a critical safety calculation. It really makes you think, doesn't it? What other default settings are lurking inside the complex tools we use every single day that are quietly shaping our results, maybe in ways we don't even realize?